For half a century, deep space was silent. We believed humanity's greatest adventure was over, that we would never return to the moon. But we were completely wrong. Tonight, 4 astronauts are about to shatter that silence from the top of the most powerful rocket in human history. They will pass the 400,000-kilometer record of Apollo 13, reaching a staggering 405,000 kilometers away. To do this, they will have to endure a hell of nearly 3,000 degrees Celsius. But that's not the most shocking part. The one shield meant to protect them was damaged in over 100 places during its last test, and experts called this flight madness. If you feel the thrill of the risk behind this 53-year wait, then like this video and subscribe to the channel, because everything you believe is about to be shaken. Are you ready? Let's begin. For years, we saw the depths of space as an abandoned memory. It was humanity's greatest achievement. But it was as if it never happened, as if it no longer mattered. 53 years, a silence that lasted for 4.5 decades. Because after 1972, no one went back. The Apollo missions ended. The journey to the moon was a dream left in old photographs. But tonight, everything changes. Tonight, that silence will be shattered. Because this is so much more than a test flight. This is the beginning of humanity's new era in space. That is why you must understand every detail. You must know what every single piece means. First of all, to understand this mission, you need to meet 4 people. The people sitting in the 4 seats of the Integrity capsule. Because who they are is no coincidence. Each one is achieving a first. Each one is doing something that has never been done before. This is why this mission is more than just a trial run. First, there is the commander. His name is Reed Wiseman. Wiseman is 50 years old. He spent 27 years in the United States Navy. He flew fighter jets like the F-14 Tomcat and the F-18 Super Hornet. But that is not his real story. Because NASA selected him from a pool of 3,500 candidates. In 2014, he went to the International Space Station. He spent 165 days there. Yet, what defines him are the struggles he faced while preparing for this mission. Because, during this process, he lost his wife to cancer. And yet, he kept going. He became the chief of the astronaut office. This was the highest rank an astronaut could achieve. But he gave up that position because he wanted to go to the moon. So, he returned to flight status. The pilot is Victor Glover. He is 49 years old, one of the most talented fighter pilots of his generation. Because he has over 3,000 hours of flight time in 40 different aircraft. He made 400 landings on aircraft carriers. He flew 24 combat missions. But there is something else that makes him special. Victor Glover will be the first black person to travel beyond low Earth orbit. This is a monumentally important moment, because every single Apollo mission to date, those who landed on the moon and those who didn't, were all composed of only white men. After 53 years, that is changing. That is why Glover has a habit. Every Monday, Shaktiel, he listens to Gil Scott-Heron's song, Whitey on the Moon. The song was written in 1970 to criticize a government spending billions to go to the moon, while the black community couldn't get basic health care. Glover listens to this song to never forget that tension, to remember that this moment does not belong to a select few, but to everyone. Mission Specialist. 1 is Christina Koch. She is a 46-year-old electrical engineer and physicist. But her story doesn't take place in a lab, because before joining NASA, she spent years in Antarctica. She stayed for an entire winter at the Amundsen Scott South Pole Station. There, she was also part of the fire and rescue teams. She is not someone who shies away from harsh conditions. That is why she broke a record when she arrived at the space station in March 2019. She stayed in space for 328 consecutive days. This is the record for the longest single spaceflight ever made by a woman. But tonight she will do something even bigger. Christina Koch will be the first woman in history to travel beyond low Earth orbit. Think about what that means. The first human spaceflight was in 1961. Valentina Tereshkova became the first woman in space in 1963. But in over 60 years of space history, no woman has ever gone beyond the station's 400-kilometer altitude. Tonight, that also changes. The fourth member of the crew is Jeremy Hansen. He is also 49 years old, Canadian, a colonel in the Royal Canadian Air Force. But there is a detail in his story that is hard to ignore. NASA selected him in May 2009. This mission takes place in April 2026. That means nearly 17 years will have passed between his selection and his first spaceflight. 17 full years. 17 years spent in training. In waiting, voyage, with constantly postponed dates. That is why tonight, he will become the first non-American to travel beyond low Earth orbit. The first Canadian to go to the moon. 4 people, each one breaking down a wall. A commander who gave up the highest rank to fly. A pilot who never forgets this moment belongs to everyone. An engineer who spent 328 days in space and still wanted more. And a man who had the hardest conversation with his family and waited 17 years. But you cannot fully grasp the magnitude of this mission without understanding the machine that will carry these 4 people 5,000 kilometers away. Because what will take them there is the most powerful rocket humanity has ever seen. This rocket is called the SLS, the Space Launch System. It stands 98 meters tall. What does that mean? Think of it this way. The Statue of Liberty, from its base to the tip of its torch, is 93 meters. The SLS is taller. But it's not its height that makes it historic. What makes it historic is what happens the moment it ignites its engines. Because now, at liftoff, the SLS generates a massive 8.8 million pounds of thrust. That's a force of about 40 meganewtons. This is 15% more thrust than the Saturn V rocket, meaning it's a machine more powerful than the legend that held the title of the most powerful rocket for 50 years. Tonight, when the SLS launches, it will be the most powerful crewed rocket launch in human history. But here's the interesting part. Much of the technology that makes this possible is not actually new. It is technology that already existed, that had worked before, and that someone wisely decided not to throw away. Let's start with the giant cylinders on either side of the rocket. They are the solid rocket boosters. Each one is 54 meters high. That's equivalent to a 17-story building. And each one alone produces 3.6 million pounds of thrust. Let's put that number in perspective. One of today's most used rockets, the SpaceX Falcon 9, produces 1.7 million pounds of thrust at liftoff. A single booster on the SLS produces more than twice that. And there are two of them, because these two boosters provide more than 75% of the rocket's total thrust for the first 2 minutes of flight. They are the power that rips this monster off the ground. At the center is the core stage. It's about 65 meters tall. Inside, it carries something incredible. Over 2,800 liters of cryogenic fuel. Liquid hydrogen at minus 253 degrees. Liquid oxygen at minus 183 degrees. These are extremely cold temperatures. That is why the tank's orange color is not paint. It's an insulation foam applied to keep the fuel at these freezing temperatures in the Florida heat. But the real story is at the base of this stage. There sit 4 EARS-25 engines, and these engines have a history. Because the EARS-25s were the engines that powered the Space Shuttle program for 30 years, from 1981 to 2011. When the shuttle program ended, NASA made a brilliant decision. It saved the engines. It put them in storage. And when it was time to build the SLS, it brought them out again. The 4 RS-25 engines that will fire tonight are actual shuttle engines that have been to space before. But these engines have a capability that the solid rocket boosters do not. They can pivot in any direction by up to 8 degrees. This allows the rocket to correct its course. It allows it to compensate for wind. Without this ability, the SLS would just fly straight up. But when you're carrying people to the moon, flying straight is not enough. When all these pieces come together, an unprecedented power emerges. But this power only carries the astronauts to orbit. The rest of the journey will be spent inside another engineering marvel that will be their home for 10 days. Because these 4 people will live in a place very different from the Apollo capsule. And that difference is critical for their survival. Because every system, every valve, every sensor on this mission is designed not just to get them to the moon, but also to bring them back. And that return journey holds the mission's biggest unknown. That is why we must look closer at that home. The Integrity capsule. Because that conical structure sitting atop this incredible rocket is not just a transport vehicle. It is a life support unit in deep space, a science laboratory, and ultimately, the one shield that will bring 4 people back to Earth through fire. And the story of this shield is the most controversial topic of the mission. But before we get to that controversy, we need to understand what life is like inside this vehicle. Because spending 10 days in space is not just about getting from one place to another. It is a completely different way of being. And the rules of this existence within the walls of that capsule. Because within the walls of that capsule, life is unlike anything we know. The 3 astronauts of Apollo 8 orbited the moon in December of 1968. They did it inside a capsule roughly the size of a family car. 3 grown men in survival suits, a few days' worth of food, and all the tools needed for a lunar mission. All in a space so cramped that no car manufacturer today would pass its safety tests. And that is why Commander Frank Borman described the journey this way. We were so cramped that when one of us moved, we all felt it. The Orion capsule, however, has a diameter of 5 meters. But Apollo's diameter was less than 4 meters. On paper, this might not seem like a huge difference. Yet, in terms of habitable volume, it means 57% more space. This extra space is critical because it is precisely what allows 4 people, instead of 3, to survive for 10 days without losing their minds. the crew named their capsule Integrity. It's not a flashy name, but it says a lot about the philosophy of this mission. Now, we need to understand what it means to live inside Integrity for 10 days. Because this is not a space station. It has no extra modules, no separate living quarters. It is basically an inverted cone, a place where 4 people eat, sleep, and exercise, a place where they even go to the bathroom and work, all in the same space, the size of a large minivan, and all of it at least 100 kilometers from Earth, and eventually 405,000 kilometers away. Let's start with the basics, the toilet. Apollo astronauts used plastic bags for solid waste, and a flexible tube system for urine. But in a zero-gravity environment, this simple act becomes a huge engineering problem. That is why the Integrity capsule carries the Universal Waste Management System, which is almost identical to the system on the International Space Station. It has a small door for privacy. The system uses a constant flow of air to separate and contain waste. This is a huge improvement over Apollo's plastic bags, so for exercise. Integrity carries a compact flywheel device called Rocky. It's only the size of a briefcase. But with a cable and pulley system, it allows for exercise with up to 180 kilograms of resistance. The crew must use it for 30 minutes a day, because in zero gravity, muscle and bone, tissue deteriorate rapidly. The food is dehydrated. It's heated on a small warming plate. The water comes from the service module outside, 240 kilograms of drinking water. This water doesn't need to be recycled, because, the mission is short enough. But the thing that houses all these life support systems and the main engine is not the capsule itself. It is the European Service Module. Built for the European Space Agency by Airbus in Bremen, Germany, located beneath the capsule. This is the ship's powerhouse. It's the part that contains the main engine, the maneuvering thrusters, the solar arrays, and the oxygen and water supplies. The 4-winged solar arrays have a total wingspan of 19 meters. They generate enough electricity to power 2 average American homes. This is also the part that will separate and burn up just before re-entry into the atmosphere. Only the conical capsule of Integrity will return to Earth. And this is where we come to the issue of the heat shield. On the bottom of the capsule, the surface that will face Earth during re-entry, there is a material called avcoat. It's an ablative composite, meaning it is designed to burn away in a controlled manner. Because when the capsule hits the atmosphere at 40,000 kilometers per hour, it needs to absorb and dissipate the extreme heat that is generated. At that moment, the temperature will reach 2,760 degrees Celsius. For comparison, steel melts at 1,500 degrees, titanium at 1,670 degrees. Avcoat must withstand nearly twice these temperatures for minutes on end. It must protect everything, including the 4 people inside. But there's a problem, because the avcoat on the Artemis I mission did not behave exactly as expected, which brings us to the most serious controversy surrounding this mission. Before understanding the depth of that controversy, you must know exactly what Integrity will do during these 10 days, because re-entry is the final act. But before that final act, there are 9 days during which these 4 people will do things no human has done in over half a century. And it all begins tonight at 12:24 a.m. At that time, the SLS rocket launches. 8 minutes and 6 seconds later, the core stage engines shut down. The upper stage takes over. And 20 minutes after launch, the Integrity capsule is alone in space for the first time. But they are not going directly to the moon. Not yet. The first thing Integrity does is enter a very special Earth orbit. This is not the 400-kilometer low Earth orbit of the International Space Station. This orbit is elliptical, like an elongated egg, and at its lowest point. It is 185 kilometers from Earth. At its highest point, it reaches 70,000 kilometers. 70,000. This means, by the time the Artemis II crew completes their first full orbit around the Earth, they will have already reached a distance no human has reached in decades, and they haven't even started their journey to the moon. They spend about 2 days here. This is a critical time. Because, during these 2 orbits, the crew checks absolutely everything: the life support system, the navigation system, communications, the pressure suits. If something goes wrong at this stage, the mission can be aborted relatively safely. Because they are still close to Earth, there are still options. But something else of immense importance for the future of the program happens during these 2 orbits. Then about 3 hours and 24 minutes after launch, Integrity separates from the rocket's upper stage. At that moment, Victor Glover takes manual control of the ship. What he does is a maneuver that looks simple from the outside, but requires extraordinary precision in practice. The capsule turns 180 degrees, facing the upper stage it just left behind. Glover manually guides the capsule towards it, first to 90 meters, then to 9 meters. A distance of only 9 meters between his own ship and a multi-ton metal structure traveling at 28,000 kilometers per hour. They will not dock. Because the upper stage has no docking port. What Glover is doing is rehearsing the proximity maneuvers that future missions will need to dock with the lunar module in orbit near the moon. Because the return to the lunar surface on Artemis III will work exactly like this. The Orion capsule will arrive at the moon, dock with SpaceX's lunar lander. 2 astronauts will descend to the surface, return, dock with Orion again, and then they will all return to Earth together. If that docking fails, the mission is over. That is why Glover is rehearsing those maneuvers tonight. After all these checks and rehearsals are complete, the most important moment of the first 2 days arrives, and this moment puts the crew on a path of no return. Because, as they pass through the lowest point of their orbit, the main engine of the European service module ignites, and from that moment on, they are no longer orbiting the Earth. They are heading for the moon. But this journey follows a much smarter route than a simple straight line, and that route will be their life insurance. However, to understand what this ingenious orbital plan is and why it's so critical, we must first grasp what the journey itself means. Because this isn't just about getting from point A to point B. This is a delicate dance of physics and gravity. And every step in this dance is a result of painful lessons learned decades ago. And the most important of these lessons is hidden in that clever route, because it's no different from a simple insurance policy. The thrust that launches the astronauts to the moon doesn't just send them to their destination, it also puts them on a path that will bring them back home. Welcome to the shocking world of what was discovered for and what is about to happen. But everything was planned, everything was calculated. But Some things can't be fully known until they are experienced. The first shocking fact is the route itself. It's called a free return trajectory. What does this mean? It means an incredibly precisely calculated orbit. If the engines were to stop working at that moment, the moon's gravity alone would capture the capsule and fling it back to Earth, without any additional burns, without any crew intervention. Physics takes over. This is not a theory, because Apollo 13 lived it. In 1970, when an explosion disabled their ship 320,000 kilometers from Earth, it was precisely this that guided them home. The moon's gravity. The Artemis II crew is traveling on this very same safety net. That is why that first major burn, the one that lasts 6 minutes and 5 seconds and increases the ship's speed by 1,450 kilometers per hour, not only sends them to the moon, but also gives them a guarantee of returning home. This is genius, born from a painful lesson. But that's not the most chilling moment of the journey. On the 6th day, Integrity will arrive near the moon. They will not enter orbit. They will not approach the surface. The route will take them around the far side of the moon, the hemisphere that never sees Earth. And at that very moment, for about 30 to 50 minutes, the moon will come between Integrity and Earth. Communication will be lost. No signal. No mission control. No one. 4 humans. Behind the moon. Completely alone. Farther away than any human in history. Even this distance is mind-boggling. Because Apollo missions orbited at an altitude of 100 kilometers from the surface. 100. But Integrity will pass by the lunar surface from a distance of 6,000 to 9,700 kilometers. In that moment of absolute silence, gravity will do its work. It will bend the ship's trajectory. It will reorient it. And when Integrity emerges from the other side of the moon, it will no longer be moving forward. It will be returning home. And at that moment, another record will be broken, an absolute record, because the maximum distance Integrity will reach from Earth will be 405,000 kilometers. This is a world record. Apollo 13 unintentionally reached 400,000 kilometers when the explosion sent it further than planned. Since 1970, for 56 years, this was the farthest point a human had ever reached from Earth. It was an accidental record, so tonight, that record will be broken deliberately. Those 4 astronauts will become the farthest humans from Earth in history. But all these records, all these maneuvers, they are all preparation for a single moment. The part of the mission that no one can fully rehearse. The 10th day, re-entry, and here Mole. That unsettling debate about the heat shield returns with full force. Because what happened on the Artemis, one mission was not a small problem. It couldn't be. This is the mission's biggest unknown. When the uncrewed Orion capsule of Artemis I splashed down in the Pacific Ocean on December 11th, 2022, the mission was celebrated as a success. But then, engineers examined the heat shield, and what they found did not match the models. The AVCOAT material had not eroded uniformly and gradually as it should have. Instead, there were over 100 spots where pieces of material, some the size of bricks, had suddenly broken off. A surface riddled with charred divots. This should not have happened. The simulations had not predicted it. 2 independent heat shield experts said they would not have returned in that ship. One even stated that what NASA was proposing to do was insane. So why? Why did the shield behave this way? Because the capsule will hit the atmosphere at 40,000 kilometers per hour. At that moment, the temperature will reach 2,760 degrees Celsius. That is nearly twice the melting point of steel, 1,500 degrees Celsius. That shield has one job: to protect the 4 people inside from that inferno. But in the previous test, the shield had unexpectedly disintegrated. How could that inspire any confidence? NASA analyzed the data, and they redesigned the re-entry trajectory, and they made the decision to fly. Commander Reed Wiseman said, "I trust the work of our engineers." But one of those experts, Charles Kamada, was still not convinced. He was an astronaut who flew on the first shuttle mission after the Columbia disaster. He knew heat shields, and he said he would not get on that ship. This is the tension of tonight, the tension between a situation where the data says the structure will hold, and one where experience says this is madness. But the real question is why? Why didn't that shield behave as expected? The answer NASA found after more than a year of investigation was both surprisingly simple and based on a detail no one had anticipated. The problem wasn't the material itself. The problem was the specific re-entry trajectory NASA had designed for Orion, a maneuver known as a skip entry. And the unexpected physical effect created by this maneuver had changed everything. Because when the capsule entered the atmosphere once and then skipped back out into space, because when the capsule entered the atmosphere and then skipped back out into space, something unexpected happened. When the capsule briefly exited the atmosphere, the heating rates decreased dramatically. The ablative material stopped losing heat to the outside. But the intense heat that had already soaked into the avcoat blocks was still there. It was building up inside. The gases normally formed during the process needed to escape. But in this intermediate phase, they couldn't. So, the internal pressure increased, and the blocks cracked. They broke off irregularly. No simulation model had predicted this, because no one had ever attempted a double-dip re-entry with this material at return speeds from the Moon. The Apollo missions used a simpler, harsher, but more predictable direct re-entry. That is why NASA made a fundamental decision. For Artemis II, they eliminated that double-dip re-entry. Integrity will not skip. It will enter more directly, with a steeper trajectory. This will create a higher peak temperature, but for a much shorter duration. According to the models, this will cause the Eve coat to crack much less, meaning the specific problem that caused the damage on Artemis, one should not be repeated. And yet, an expert called it madness, and that word will follow them like a ghost throughout the mission. But the shield is not the only surprising and dangerous thing on this mission. The science the crew will conduct is just as groundbreaking, and at its center is radiation. Because Apollo astronauts carried 2-meter-long film strips to measure radiation. After the flight, these films were developed, and only then did scientists understand how much radiation the astronaut had received. But during the mission, no one knew anything. On Artemis II, however, each crew member carries a digital dosimeter in their pocket that transmits real-time data. This is revolutionary, because on the International Space Station, astronauts are partially protected by the Earth's magnetic field. But in the orbit of Artemis II, outside of that protection, the radiation exposure rate is 2 to 3 times higher per unit of time. this is not fatal for a 10-day mission. But if you are planning a 7-month journey to Mars, you need to understand exactly what that radiation does to the human body. This mission is laying the foundation for that understanding. Yet, that's not the most extraordinary experiment traveling on integrity. That is something that sounds like science fiction. Its name is Avatar. This stands for living cells traveling inside the capsule. In devices the size of a USB stick, stem and progenitor cells taken from bone marrow. But these are not just any cells. These are cells obtained from platelet samples donated by each of the 4 astronauts before the mission. These cells are kept at 37 degrees Celsius in an autonomous laboratory the size of a shoebox. For the 10 days of the mission, they will be exposed to the exact same conditions as the astronauts themselves. The same microgravity, the same radiation, the same deep space environment. These are literally Maltschek miniature organs of each crew member, traveling with them beyond Earth orbit. So why bone marrow? Because bone marrow is one of the most radiation-sensitive tissues in the human body. This means damage that affects the immune system, oxygen carrying capacity, and blood clotting. That is why understanding how this tissue is affected is vital for deep space missions. And this technology is traveling beyond the Van Allen belts for the first time. But there is another radiation danger, and the crew must manage it very concretely during their journey. Solar storms. The sun periodically ejects massive clouds of charged plasma into space. These are clouds of energetic particles moving at millions of kilometers per hour. If one of these storms hits integrity in deep space, the radiation exposure rate could multiply within a few hours. We are currently at the solar maximum, meaning here's the peak of the sun's 11-year activity cycle. So, the chance of a storm is not impossible. So, what is the crew's emergency plan? A protocol that NASA engineers describe as a little pillow fort. There is no dedicated radiation shelter. But there is a protocol. If sensors detect a solar flare heading towards the ship, the crew takes out storage lockers, food bags, water bags, and spare equipment, and they strategically place them around their bodies to create an additional mass barrier, as it takes them about an hour to build this shelter, and they may need to stay inside for up to 24 hours. Mass, any kind of mass, absorbs radiation. It's not perfect, but it's enough. All of this, the real-time dosimeters, the organs on a chip, and the pillow fort, is part of something bigger than this flight itself, because every piece of data collected on this mission is a brick added to the knowledge base needed to send humans to Mars. But all these technical details, all these risks in scientific experiments, bring one big question to mind. Why? Why are we going back? And what's different this time? Because the destination after the moon is much farther away, and to get there, we must first learn to use the moon as a stepping stone. But exactly how that stepping stone will be built, and which technologies will make it possible, will determine the fate of future human space exploration, and the foundations of those technologies are both surprisingly familiar and entirely new. But how exactly do these technologies work? What engineering marvels lie behind the shocking discoveries and audacious goals? Let's shift gears now. Let's move out of the fast pace and into the heart of the machine that makes this mission possible. Into the technical details. Because what makes the Artemis program different is not just its goals, but the methods it uses to achieve them. That is why understanding how each part works is to decipher the codes of future space exploration. It all starts with the rocket. The SLS Mutschat, the Space Launch System. We know what makes it special is its raw power. But how is that power produced and controlled? The secret lies in a clever combination of two different technologies. Think of those giant white cylinders on the sides of the rocket. They are the solid rocket boosters, SRBs. You can think of them as giant fireworks. Once ignited, they continue to burn until their solid fuel is completely exhausted. They cannot be shut down, they cannot be controlled. They just produce pure, marchastic, unstoppable power. Each is 54 meters tall, and together, they provide more than 75% of the total thrust at liftoff. This enormous power allows the rocket to push through the densest part of the atmosphere in the first 2 minutes. But this raw power has a price, because it is uncontrollable. This is where the rocket's core comes into play, the core stage. At the base of this stage are 4 ELRS-25 engines. These are liquid-fueled engines. They burn liquid hydrogen at -253 degrees and liquid oxygen at -183 degrees. This gives them a capability that the solid rocket boosters lack. Control. These engines can adjust their thrust levels and even pivot at an angle of up to 8 degrees. This pivoting ability is called thrust vector control, just like turning the rudder of a boat. It allows the rocket to precisely adjust its direction. So, in the first 2 minutes of liftoff, the solid rocket boosters provide the brute force, while the AR-S-25 engines provide the fine-tuning. They compensate for wind, correct the trajectory, and 2 minutes later, at an altitude of 50 kilometers, the solid rocket boosters finish their job and separate. From that moment on, the mission is entirely under the control of the RS-25 engines. This hybrid approach, combining both the raw power of the Saturn V and the controllability of the Space Shuttle, offers the best of both worlds. It is a smart balance between cost and performance. So how do these engines produce this incredible power, especially the RS-25s? Their secret lies in an extremely efficient design called a staged combustion cycle. Think of a conventional rocket engine. Fuel and oxidizer combine in the combustion chamber, or explode, yet coals, and the resulting hot gases are expelled through the nozzle to create thrust. But the turbines that run the fuel pumps in this process also consume some fuel and usually vent their exhaust outside. This is a waste. The RS-25 works differently. It uses a two-stage combustion process. First, a small portion of the fuel is burned in a rich mixture in two small chambers called pre-burners. This is not a full combustion. It just produces enough hot gas to drive the pumps. This hot gas drives the turbines that spin the massive fuel and oxygen pumps hundreds of times per second. But here is where the genius begins. The hot gases from those turbines are not vented outside. Instead, they are routed into the main combustion chamber, and there, they combine with the rest of the fuel to create the main big explosion. The thrust. What does this mean? It means every single drop of fuel the engine uses is ultimately used to produce thrust. Nothing is wasted. That is why the RS-25 is one of the most efficient rocket engines in history. It provides incredible thrust for every kilogram of fuel it burns. This efficiency means being able to do more work with less fuel, which means being able to carry heavier payloads farther. This was exactly why NASA saved these engines when the Space Shuttle program ended. Because they were engineering marvels that offered a perfect balance between reusability and raw power. And now, those marvels are taking humanity back to the moon. Atop this rocket is the Orion capsule, and one of its most critical systems is the Environmental Control and Life Support System, ECLSS, which makes life in space possible. In the Apollo missions, this system was quite simple. The astronauts breathed pure oxygen, and carbon dioxide was absorbed by lithium hydroxide filters. Water was not recycled. This was sufficient for short missions. But Artemis aims for long-duration stays and eventually a journey to Mars. So, Orion's life support system is much more advanced. Just like on the International Space Station, ISS, Orion uses a closed-loop system. This means resources are recycled. For example, the system that removes carbon dioxide from the air. The astronauts breathe sends this carbon dioxide to a reactor. In this reactor, the carbon dioxide is combined with hydrogen obtained from the ship's water through electrolysis. This chemical process, called the Sabatier reaction, produces water and methane. The produced water can be reused for drinking or electrolysis, while the methane is vented into space. This system recovers about 1 kilogram of water every day. This means less water needs to be carried from Earth. Less water means less mass, and less mass means a more efficient mission. Urine recycling will not be used on a short mission like Artemis II. But the system has this capability because, on future long-duration, Moon or Mars missions, recycling every drop of water will be vital. This closed-loop philosophy represents a fundamental break from Apollo's throwaway approach. It is a technical reflection of the goal to establish a sustainable presence in space. However, all these complex systems, the rocket and the capsule, sounds need to work together in harmony. And what ensures this is the launch and orbital mechanics itself. A moment that occurs just seconds before launch is the best example of this delicate orchestration. At 6.36 seconds before liftoff, the 4 RS-25 engines on the core stage ignite, but the rocket is still attached to the launch pad by massive bolts. During these 6 seconds, the engines reach full power and the onboard computer systems analyze thousands of data points to verify that everything is working perfectly. If the slightest anomaly is detected during this 6-second check, the launch is automatically aborted. The engines are shut down. But if everything is okay at the exact moment of 0, the solid rocket boosters ignite, and the 6 hold-down bolts on the launch pad explosively release. This sequence is critical, much because the liquid-fueled AEMRS-25 engines can be shut down if there's a problem. But once the solid rocket boosters are ignited, there is no going back. So, the controllable system is tested first. Everything is confirmed to be okay, and only then is the irreversible step taken. This is a philosophy of verify first, then commit, instead of commit first, then verify. This simple but vital safety logic is designed to minimize risks from the very beginning of the mission. This rocket is not just powerful, it's also smart. But the most controversial of these smart systems comes into play during re-entry. And understanding how that system works is the key to grasping what went wrong on Artemis I, and why NASA chose a different path for Artemis II. Because the story of that shield is not just a lesson in materials science, it is also a lesson on risk, innovation, and engineering judgment. And the details of that lesson offer the key to understanding the heat shield problem. Because the issue was less about the material itself and more about how it was treated. The skip entry trajectory that NASA designed for Artemis I was in theory ingenious. Just like skipping a stone on a lake, it involved the capsule entering the upper layers of the atmosphere, partially slowing down due to friction, and then using aerodynamic lift to briefly skip back out into space. The purpose of this maneuver was to allow the capsule to land more precisely in a smaller area of the ocean. This would reduce the time and cost of recovery operations. It sounds great. But physics had prepared a surprise no one expected. When the capsule first plunged into the atmosphere at 40,000 kilometers per hour, the EVE coat material overheated. This was normal. But when it skipped back into space, in that brief moment of breathing, everything changed as the temperature of the external environment suddenly dropped. The surface of the shield began to cool. Yet, the immense heat that had soaked into the material was trapped inside. The hot gases that should have normally been vented during the ablation process found nowhere to go due to this cooling outer layer. So, the pressure inside the EVE coat blocks increased dangerously, and this internal pressure caused the material to crack and break off in irregular chunks. The Apollo missions never experienced this, because they used a simpler EOS, single-shot, direct entry. It was a harsher breaking, but it was much more thermally predictable. That is why NASA completely cancelled this skip entry for Artemis II. The capsule will make a single uninterrupted dive at a steeper angle. This will cause a higher peak temperature. But the duration of exposure to this temperature will be significantly shorter. According to the models, this simpler approach will prevent the internal pressure buildup and irregular breakoffs seen on Artemis I. This means reverting to a simpler, more tested solution in the face of a known risk. In engineering, sometimes this is the wisest move. However, the heat shield is not the only shield protecting the astronauts on this mission. In deep space, there is a more insidious enemy: radiation, and the line of defense the crew uses against this enemy is both surprisingly simple and multi-layered. The main line of defense is the capsule itself and everything inside it. Mass absorbs radiation. This is a basic rule of physics. So, the ship's walls, equipment, water tanks, and even the astronauts' own bodies provide constant protection. But the sun can send out massive energy bursts, solar storms, at unexpected times. If such a storm were to hit the ship, radiation levels could rise to dangerous levels. This is where the pillow fort comes in. This is not an official engineering term, but the logic is exactly that. When the astronauts receive a storm warning, they take all the movable mass inside the ship, food bags, spare equipment, clothes, and use it to build a small shelter for themselves in the center of the capsule. This is a process that takes about an hour, and they may need to stay behind this additional mass barrier for up to 24 hours. This is a completely new protocol that was not present in the Apollo missions, because the Apollo missions were shorter and were planned during periods of lower solar activity. Artemis I, however, aims to keep people in space for months. So, these kinds of temporary but effective solutions are a vital rehearsal for future Mars journeys. The methods of scientific data collection are also revolutionary compared to the Apollo era, especially in measuring the biological effects of radiation. See, Apollo astronauts carried passive dosimeters. These were basically small film strips that darkened as they were exposed to radiation. After the mission, these films were examined and the astronaut's total radiation dose was calculated. But this was like performing an autopsy. You only found out what happened after it was too late. The Artemis II crew, on the other hand, carries active dosimeters called the Hybrid Electronic Radiation Assessor, HERA. These are advanced devices that measure the type and energy of each radiation particle in real time and send the data instantly to Earth. But the real revolution lies in the Avatar experiment, those miniature organ-on-a-chip devices traveling in the capsule. Inside these devices are the bone marrow stem cells of each individual astronaut. This is incredible because, for the first time, scientists will be able to study exactly how a person's biological tissue reacts when exposed to the deep space environment, while that person is still in space. This is the beginning of personalized space medicine. This is a capability that was unimaginable during the Apollo era, because with this, we will be able to model the cellular damage caused by radiation, the immune system responses, and potential cancer risks based not on assumptions, but on data obtained directly from human tissue. This is the key to one of the biggest puzzles we need to solve if we want to go to Mars safely. All these technologies, the hybrid rocket engines, the closed absolute disconnection that will last for 30 to 50 minutes, no mission control, no voices of their families, nothing. Just 4 humans and the infinite darkness of space. In that moment, every human who has ever existed, lived, or will live, every animal, every plant, every memory, every war, every peace, everything, is on a tiny blue dot behind that massive grey rock, and they are outside of that dot. What could that feeling be like? How does this absolute solitude feel? This is an experience no simulation can teach, no book can describe. And in this silence, gravity does its final job. It bends the ship, it changes its direction, and when integrity emerges from the other side of the moon, it is no longer moving forward, it is returning home. But these records, these maneuvers, these mind-bending moments were all preparation for one thing. Because when those 4 people looked out those small windows, they weren't just performing a technical mission. They were experiencing something that would change humanity's perspective forever. What they saw was not just a view, it was an enlightenment. And the details of that enlightenment. And the details of that enlightenment explain why this entire mission is so important. Because what they saw wasn't just the moon or the stars. What they saw was Earth. But an Earth as no one had ever seen it before. That is why this mission is so much more than an expedition. It is a change of perspective, a moment that recalibrates humanity's view of itself. And this moment begins with the rebirth of one of history's most iconic images. December 24th, 1968, Apollo 8. Astronaut Bill Anders looked out the command module window, and he saw it, something no human had ever seen before. A full, whole Earth rising above the grey, lifeless lunar horizon. A blue marble, swirling with white clouds, a fragile jewel suspended in the middle of darkness. He took a photograph in that moment. It was named Earthrise, and that single frame changed everything. It changed humanity's view of itself forever. Because, before that photo, Earth was the world. It was everything. An infinite place with no boundaries. But, after that photo, Earth was small, it was fragile, it was limited. It was a single hole where borders were meaningless. The Artemis II mission patch is a direct reference to that photograph. The same cloud patterns, the same composition. This is not nostalgia. This is a statement of intent. Because this mission is also designed to create a new Earthrise moment. But this time, with a difference that will change history. This time, there's an iPhone. At first, this might sound like a trivial detail, but it is not, because one of those 4 astronauts, while 405,000 kilometers away, will look out that window, and they will see the same view that Anders saw. But this time, they will take a picture with that device in their pocket, and that image will reach Earth almost instantly. No waiting for a roll of film to be developed. No waiting for the mission to end. That image, taken by the most distant humans in history with a device we all have in our pockets, will drop directly into social media, news feeds, our phones. How is this possible? An instant photo from 400,000 kilometers. Because deep space communication technology has evolved exponentially since the Apollo era. This has the potential to create an earthquake in humanity's collective consciousness. Because Anders' photo changed the world because people saw it in newspapers, in magazines. But this new image will be lived in real time. This is the democratization of space exploration. This is the first time in history that humanity's greatest adventure will unfold, moment by moment, before all of our eyes. But the distance record is not the only record being broken on this mission. What's also being broken is a record of silence. 53 years, more than a generation. Those lost years when humanity turned its back on deep space. In 1972, as the last Apollo astronaut, Gene Cernan, left the moon, he said, "As we leave the moon at Taurus Littrow, we leave as we came, and, God willing, as we shall return, with peace and hope for all mankind." It was a promise. But for 53 years, it was an unkept promise. Yet tonight, that promise is being fulfilled. But this return is different from the spirit of Apollo. Apollo was a race, an effort fueled by the fear of beating the Soviet Union. And when the fear disappeared, the program vanished with it. This time is different. This time, there is no enemy. This time, there is a plan built over decades, a plan supported by international partnerships. Because, on Artemis II, there is a Canadian astronaut, Jeremy Hansen. He will be the first non-American to go to the moon. This is part of a deal made in exchange for the robotic arm Canadarm3, which Canada provided for the program. 61 countries have signed the Artemis Accords, which set the rules for the exploration of the moon. This is the most international space exploration program in history, even more international than the International Space Station. How could this be possible? How could a space program born from the ashes of the Cold War turn into such a global collaboration? Because the goal is no longer to beat a superpower. The goal is to advance humanity itself. This is not an earthquake in the world of science. This is a geopolitical earthquake. The moment space exploration shifts from competition to cooperation. And the most tangible proof of this cooperation lies in the future. Artemis III. This will be the first lunar landing mission since 1972, and this mission will not follow in Apollo's footsteps. It will go to a brand new region, the south pole of the moon. Because Scientists believe there is frozen water ice in the permanently shadowed craters there. This is a game-changing discovery, because that water ice can be split into two things: oxygen to breathe and hydrogen for rocket fuel. How could this be possible? Building a gas station on the moon. Yes, exactly that. A base on the lunar surface that can produce its own fuel completely changes the economics of space exploration. Not everything needs to be transported from Earth anymore. This makes the moon not just a destination, but a stepping stone on the way to Mars and beyond. One of the 2 astronauts who will land on the moon in Artemis I will be the first woman in history. The other will be the first person of color. This is not just a symbolic gesture. This is the answer to the song Victor Glover listens to every Monday. This is proof that space no longer belongs to a specific group, but to all of humanity. The earthquake in the world of science will happen when the existence of that water is confirmed. Because, in that moment, it will be understood that the moon is not just a barren rock, but also an invaluable resource. All these plans, all these technologies, all these records, they all serve one ultimate goal: Mars. Because the real purpose of the Artemis program is not the moon. The moon is a proving ground. The moon is where humanity will develop the technologies, protocols, and psychological resilience needed to go to Mars. A round trip to Mars takes at least 2 to 3 years. Humans have never been in space for that long before. Bone loss, muscle atrophy, radiation damage, psychological isolation. These are all huge problems that don't yet have a complete solution. The moon will be the laboratory where we find those solutions. Because the moon is only a 3-day journey away. If something goes wrong, there's a chance to come back. But on Mars, there is not. Once you set off for Mars, there is no such thing as a rescue mission. That is why establishing a permanent base on the moon, living on the surface for weeks in pressurized rovers developed by Japan and Toyota, building surface habitats, is a final check that must be done before committing to a Mars mission. When Commander Reed Wiseman was asked why this mission is important, his answer was simple: 5 words. Because we want to see people on Mars. This is the summary of the entire program. This is the end of 53 years of silence and the beginning of humanity's greatest adventure. But now, after all these epic moments, these record-breaking achievements, and these audacious plans for the future, it's time to pause and think, time to slow down and turn to philosophy. Because all this technology, all this science, exists to answer one fundamental question. So what does all this mean for us? For us on this small blue planet? And now, after all these epic moments, these record-breaking achievements, and these audacious plans for the future, it is time to pause and think, time to slow down and turn to philosophy. Because all this technology, all this science, exists to answer one fundamental question. So, what does all this mean for us? For us on this small, blue planet? What is the true meaning of this journey? And now, we face the most important question on this infinite stage of the universe. Where exactly is our place? What does this mission tell us about ourselves? On one hand, there are the massive machines we have built, the 98-meter-tall SLS rocket, one of the most complex and powerful structures ever made by humans. We use it to travel 405,000 kilometers away, to the farthest point in human history. This is a show of force that pushes the limits of the mind, a triumph of our will and intellect. But On the other hand, there is a truth we reach at the end of that journey. The moment we look out that window and see that tiny blue marble, a marble that contains all of human history, all wars, all loves, all memories. In that moment, we understand just how meaningless all our power and greatness truly is. How can it be that our ability to build one of the universe's most powerful rockets, Yachin's, only confronts us with the reality of how small we are? This is humanity's greatest paradox, discovering our weakness through our strength. The tragic reality is we are truly very small. This 405,000-kilometer journey is an epic for us. But on the scale of the universe, it's not even the movement of a grain of sand by a millimeter. Just 1.3 light seconds. The nearest star, Ma'ikaswo, Proxima Centauri, is 4.2 light-years away from us. If we tried to go there with the LS, the journey would take tens of thousands of years, and that's just our closest neighbor. When you consider the 93 billion light-year diameter of the observable universe, our existence occupies less space than a single water molecule in the ocean. This is a dizzying sense of nothingness. The fact that we can never cross this cosmic ocean, no matter how hard we try physically, carries a certain sadness. But this is where that but moment comes in. We may be physically small, but our consciousness is infinite. The reason we go those 405,000 kilometers is not to physically conquer the universe. It is to understand it. And looking at Earth from that distance shows us not the vastness of the universe, but how precious and unique that small place we call home is. The power of that Earthrise photo comes not from the size of space, but from the smallness and fragility of Earth. In that moment, we understand that all these massive journeys are actually a way of coming home, a way of understanding the value of our own planet. You are like that too. You are at the center of your own life. Your worries, your dreams, your pains feel enormous to you. But seen from that distance, you are also one of the billions of sparkles on that blue marble. Your story is part of humanity's common story, and this smallness does not make you meaningless. On the contrary, it makes you a part of that priceless whole. And then we confront time itself. On one hand, there is a universe that has existed for 13.8 billion years. Eternity stretches before and after. The timescale of mountains, stars, and galaxies is beyond human comprehension. But, on the other hand, there are our short lives, an average of 80 years, a moment that passes in the blink of an eye. Jeremy Hansen waited 17 years for his first spaceflight. That is a significant portion of his adult life. The promise Gene Cernan made when leaving the moon took 53 years to be fulfilled. An entire generation was born, grew up, and grew old in a world where humanity did not go into deep space. How is it that we, as such temporary beings, dare to touch something so timeless and eternal? Is this not the most poignant contrast of our existence? The tragic reality is that our time is so brutally limited. We are less than a footnote in the story of the universe, a spark that flashes for a moment and then dies out. Even the greatest civilizations we build, the deepest marks we leave, will be erased by the winds of cosmic time. This truth can make all our efforts seem futile and meaningless. It can create a sense of sadness, because no matter what we do, we cannot resist the overwhelming power of time. But this is the but moment that changes everything. Because What makes our lives valuable is not that they are infinite, but precisely that they are finite. Because our time is limited. What we fill it with matters. That 10-day Artemis II mission is nothing on the cosmic calendar. But for humanity, it is a moment of intense meaning, where a promise is fulfilled, a generation is inspired, and history is rewritten. Jeremy Hansen's 17-year wait is not a loss of time, but a testament to human perseverance and patience. Our strength lies not in existing forever, but in our ability to fit an eternity into that short moment. You are in that moment too. Your time is also passing. Every day, every hour will never come back, and this might scare you. But it can also give you strength, because this is the opportunity to make every moment precious, to make every choice meaningful. Your life is that short but priceless moment in which you write your own epic. And finally, we encounter one of the deepest paradoxes, loneliness and togetherness. On one hand, there is the absolute solitude that the 4 astronauts experience behind the moon. That moment when all their communication with Earth is cut off, when they are the loneliest people in the universe for 30 to 50 minutes. Only the sound of their own breath, and the infinite cold silence of space. This is the purest form of that deep sense of loneliness at the core of existence. But, on the other hand, that moment is also one of the most unifying moments in human history. The lonelier those 4 people are up there, the more united the billions of people on Earth are. Everyone's heart beats inside that small capsule. Everyone's hope is for their safe return. How can it be that the most extreme act of isolation can create the strongest feeling of togetherness? Is this not one of the most beautiful mysteries of the human spirit? The tragic reality is that each of us is fundamentally alone. We are trapped inside our own consciousness. No one can fully understand our thoughts, our fears, our deepest feelings. Just like the vast voids between galaxies, there are insurmountable distances between people. This is a poignant loneliness that is an inevitable part of life. But this is where the but moment takes the stage again, because we are the only species that tells stories, makes art, produces science, and goes to space to overcome this loneliness. Those 4 astronauts did not go there just for themselves. They represent humanity's curiosity, hope, and desire to be united. That mission was made possible by the Artemis Accords, signed by 61 countries. This is a triumph of cooperation, not competition, and the instant arrival of that photo, taken with an iPhone on Earth, is the most powerful symbol of how technology connects us. In that moment, we understand that realizing our loneliness is actually the first step to understanding how much we need each other. You feel lonely in your life too. There are moments when you feel misunderstood. But remember that, like those 4 astronauts, you are not actually alone. So you are one of billions of people who look at the same sky, wonder about the same stars, and share the same hopes and fears. And this common experience connects us with invisible threads. This journey strengthens those threads even more. These contrasts, greatness and smallness, eternity and transience, loneliness and togetherness, tell us something not just about the universe, but also about ourselves. But beyond these philosophical reflections, there is a more personal, deeper message that this mission whispers to each of us individually. What does this journey show us about ourselves in the mirror of the universe, and in the purest, most internal layer of that reflection? And in the purest, sharp, most internal layer of that reflection, lies the delicate balance between risk and discovery. That is why the answer to the question of what this journey shows us about ourselves in the mirror of the universe is that it shows our courage and our fragility can exist at the same time. This mission is, ultimately, an exercise in risk management. But it is also a celebration of that irresistible human impulse for the unknown. These two are inseparable. On one hand, there is the immense risk that permeates every moment of the mission, that heat shield. The shield that one expert described as madness. The shield that unexpectedly disintegrated during the Artemis I mission, but which NASA decided to fly based on their engineering analysis, and the most difficult conversation that Jeremy Hansen honestly admitted to having. The conversation with his wife and children about the possibility of not returning, or on the other hand, there is the mind-boggling courage required to sit on top of that rocket. Reed Wiseman giving up the highest rank as chief of the astronaut office for his dream of flying to the moon. Christina Koch, after spending 328 days in space, saying, "It's not enough," and going again. Victor Glover sitting in that seat to write a 53-year-old injustice and make history. How is it that when the risk of death is so tangible and real, the desire to explore can be so dominant? How can this fundamental engine of the human spirit challenge the instinct for survival? This is man's eternal struggle with his own nature. The tragic reality is that space exploration will never be safe. There will always be a risk. There will always be the possibility of not returning. The human body was not designed for this harsh environment. We are fragile creatures, dependent on the protection of this planet's thin atmosphere. And every time we step outside this protection, we are gambling with the unforgiving laws of nature. This fact can make such missions seem reckless and irresponsible. But this is the but moment that makes it all meaningful. Because what moves humanity forward is not safety, but courage. Our history is filled with the stories of people who dared to step out of their comfort zones. Explorers who crossed oceans, those who discovered new continents, scientists who fought diseases. They were all those who dared to take risks. The Artemis crew is part of this tradition. They do not deny the existence of risk. On the contrary, they accept it, they manage it, and they decide that it is worth the risk for a greater goal for humanity. That goal is not just to discover new places. That goal is to redefine what is possible. You face risks in your own life too. Maybe you're not sitting on top of a rocket, but you make choices every day. Will you choose the safe option? Or will you take a risk to follow your dreams? This mission reminds you of this. Growth begins where the comfort zone ends. And sometimes, the greatest rewards are hidden behind the greatest risks. And behind these risks lies another powerful contrast, past and future. On one hand, soon there is the legacy of Apollo that permeates every fiber of this mission. Launch Pad 39. B is the same pad from which Apollo 10 lifted off. The rocket's ARS-25 engines are the very same engines that flew the space shuttle for 30 years. The free return trajectory is a repeat of the ingenious maneuver that saved Apollo 13. The mission patch is a tribute to Apollo 8's Earthrise photo. This mission is almost haunted by the ghosts of the past. But, on the other hand, this mission is entirely focused on the future. The goal is not to plant a flag and return like Apollo. The goal is to build a permanent infrastructure on the moon, to create a stepping stone on the way to Mars, an international collaboration involving 61 countries, scientific experiments never tried before. Like organs on a chip, an exploration process shared instantly by astronauts with their personal iPhones. How can a mission be both so backward-looking and so futuristic at the same time? Can one foot be in the museum and the other in the stars? This is the nature of progress. The tragic reality is that we can never be completely free from the burden of the past. We learn from our mistakes, our failures, the limitations of our old technologies. The criticism that the SLS rocket uses old shuttle parts is a reflection of this tension. Getting stuck in the past can stifle innovation. Nostalgia can be the enemy of progress. But this is the but moment that offers us a different perspective, because the future is built on the shoulders of the past. To ignore the past is to try to reinvent the wheel. NASA's preservation of those RS-25 engines is a respect for the wisdom of the past. Learning from Apollo's lessons is the smartest way to prevent future mistakes. Artemis does not imitate Apollo, it honors it, and it continues from where it left off. This is not a break, but a continuity. It is one generation passing the torch to the next. You are a product of your own past, but you have made mistakes. You have experienced disappointments. You carry burdens. And sometimes this past can prevent you from stepping into the future. But remember that your past is also your strength. It is your experiences, the lessons you have learned, everything that makes you who you are. Do not deny your past. Understand it. Learn from it, and build your future upon it, just as Artemis is built upon Apollo. And at the end of all these reflections, one feeling remains: a promise. Reed Wiseman has a daughter. She was just a little girl when she watched the launch of Artemis I in 2022. She didn't fully understand what she was watching. But at some point in the next 10 days, her father will be 5,000 kilometers away. In the darkness, he will look at Earth from farther away than anyone in history. This mission is also this promise, not the abstract promise of Gene Cernan in 1972. A concrete promise with names, dates, and coordinates. The promise that we will not wait another 53 years to return. The promise that Reed Wiseman's daughter and her generation will grow up in a world where humanity is in deep space. Now we know. This mission is not just the launch of a rocket. It is humanity's reminder that it is small but precious, temporary but meaningful, alone but together, and fragile but brave. It is a tribute to our past and an investment in our future. The journey is almost over. From the fiery moment of launch to the silence behind the moon and the uncertainty of the return to Earth, every moment of this mission has shown us what it means to be human. Rockets and capsules are tools. But the real discovery is seeing ourselves in the mirror of the universe, and this discovery is just beginning. Because when this mission ends, we will return to the moment where it all began. But this time will be different. This time, we will have with us new questions, new dreams, and a renewed understanding of our place in the universe. And that final moment, the moment the capsule hits the ocean, will not just be the end of one mission, but the beginning of countless new ones. Because inside that capsule are not just 4 people. Inside that capsule is humanity's curiosity, hope, and inexhaustible desire to explore. And that desire will find its true meaning not when it lands in the ocean, but when it takes off again towards new destinations. Because the end of this story is really just the beginning of the next chapter. On this journey, humanity returned to the moon after 53 years. But I didn't tell you how the universe's own journey will end, because it too will one day die. Perhaps it will freeze into an eternal silence, or perhaps it will be torn apart in a final scream. On the next journey, we will explore that inevitable end. Are you